Oh, welcome back. Now let's start from the MapReduce functions in Spark. So it is just a review. We have talked about this last week. So the MapReduce functions or methods, there are two types. One is transformation and the other is action. For transformation, we have narrow transformation and wide transformation. So the difference is that for narrow transformation, after the transformation, the source of the data in partitions are all from the same data. The same partition. So it's more like a one-to-one map. And for wide transformation, the source of the data in partitions comes from different partitions or multiple partitions. So it's more like an end-to-end map, and it is actually corresponds to the shuffle operation in Hadoop MapReduce. All right. Action. So action is more like usually it's a view, or say the output of action is usually a view of the result of a set of transformations. All right. So the job is a list of transformations followed by one action. But actually, the action does not only give a view of the data. More importantly, the action is the real action. I mean, it's only action will trigger the real execution. So that is also called lazy evaluation. As I can show in this example, every time, so it's in an IPython notebook, but every time we execute a line, as long as there is no action involved, it's pretty fast, right? But when you execute the action, it actually took a little bit more time to finish the job. So hopefully by that example you can have a better understanding of the lazy evaluation and the functionality of action in Spark. So unlike MapReduce in Hadoop, Spark actually offers a set of methods with different functionalities. So that is gives us more flexibility when we design our MapReduce program, right? So for example, in transformation, for narrow transformation, we have a map, flat map, or filter, and for wide transformation, we have reduce by key or group by key or partition by. We do have different ways to manipulate data and the partitions key value pairs through these methods. And also for action, we have we have collect, we have for each or reduce, sample, count, such kind of actions. So they do have different functionalities to help us design our program. Right. So to some extent, we can say that in Spark, when we write our MapReduce program, it's more or less a combination of different methods to put them together as a pipeline to achieve our goal. Right. I don't know about you, but for myself, when I learn this part, the first impression is that is transformation equals to map and action equals to reduce? So the answer to this question is no. So let's look at the example here. We see it's the third time, right? So for MapReduce in Hadoop, such kind of procedure, we have a map here, right? We have shuffle here, we have reduce here, right? And also the splitting and getting the final result. But the same procedure for Spark, actually, here we have, this is parallelized data. And here we have a map, which is a transformation. Here we have, this should be more or less group by key. So it's another transformation. And here is reduced by key. Oh, these two together as a reduced by key is okay as well, but still a transformation. And here we get the final result, so you can take it as an action. So basically, if you so this is MapReduce in Hadoop, and this is MapReduce in Spark, right? So as you see, the transformation and transformation and action does not correspond to map and reduce. So it is important to not mix these two concepts together, right? And now let's look at combine by key. As I introduced before, there are many transformation methods in Spark, but here I just want here I take combine by key as an example. Because first, it is a fundamental operation, and it is a basis of many other functions, such as reduce by key or aggregate by key. Secondly, the design of combine by key is kind of complex, and there are many. I mean, if we can manage to understand and the function. And also write our own combine by key method, then we should be able to deal with other methods other MapReduce methods in Spark. And also the combine by key, this method is powerful enough to implement many different to achieve many different purposes. All right. So now let's look at combine by key. Now, if we look at the API, the functionality of the method is a generic function to combine the elements for each k using a custom set of aggregation functions. So it turns an RDD of key value sets, key value tuples, a list of key value tuples, into a result of the type of RDD. It's a key say tuple, a list of key say tuples. So say is a combined type, right? And the V and C can be different, but they can also be the same. All right. It has three functions: create, which are create combiner, merge value, and merge combiners. We will discuss each of them in the slides, right? Now let's come back to the slides. So as you can see, so it's from RDD of key value pairs to RDD of KC pairs, where C is the combined type. We have introduced that before. So three parameters, all of the three parameters are functions. So create combiner, actually, you need to answer the question here when you write the create combiner. So create combiner is about what is done to a single row when it is first met. And the merge value is what is done to a single row when it meets a previously reduced row. And merge combiners answers the question of what is done to two previously reduced rows. These are the purpose of three functions, and for the input and output for these three functions, the input of create combiner is v, while the output is c. Right, so because you have a single row, so it's by single row we mean a key value pair. So you have the v as the input and your output c. And for merge value, you actually have c and v as the input types. Right. This is because merge values asked what is done to a single row, which is a key value pair, when it meets a previously reduced row, which is already a KC pair. So you take this C and you take this V, so you have this CV, and you return the C as the result. And merge value happens in a partition. Now for merge combiners, the input is C and C. Actually, it's C1 and C2 because they are corresponding to the two previously reduced rows. So it's two key C pairs. So here we have C1 and C2, and the output is C. And also and please note that the merge combiners happens across partitions. So within the partition, you use merge value to merge the rows together. And after that, you merge combiners cross partitions. Right. So you take keys, the same key from different partitions together, and use merge combiners to do the merge thing. So the design of combine by key, you need to first of all decide what is C, and then because you know what is key, you know what is V, you need to firstly decide what is C, and then you need to decide the three functions here. In what order is totally up to you. You can do bottom up or top down. It's up to you. Right? But maybe it's not a good idea to start with merge value. Right? So let's take a look at some examples of how to use combine by key to solve our problems. So first example is again word count. So we all know what word count is, the objective of this task. So I just, in order to remind you the key value pairs of word count would be a word and 1 as the input. All right. So we use combine by key to count the occurrence of each word. All right. So for create combiner, again, it is we should decide what is C. Okay, so C would be the count, right? The count of the word or the occurrence of the word. So it is better to have a general idea of how to get say through v before we start to write the three functions, right? So as we know that the key is the word, original v is 1, so the c is the count. So basically you have multiple for one word, for each occurrence it has a 1 here, so you only need to add up all these ones, you can get the count. So it seems that this C comes from the sum of a set of V's. Okay, now let's look at the three functions here. So the create combiner is what is done to a single row when it is first met. Right. So here we need to convert V to C. Since V is an integer, right, and C is an integer as well, so here we actually keep V as it is. So V is 1, so after the create combiner it's still 1. And for merge value, this function answers the question of what is done to a single row when it meets a previously reduced row. So you have C and V. Remember, these are for the same key here. So you have C is the count of this word so far, and you have V, which is 1. So you will get the new C here. Then the function would be C plus V, right? And for merge combiners, answers the question of what is done to the two previously reduced rows. So it's C1, it's 2C. The output type is again C. So basically we have a C1, C2. The count, again, it's the same key. The count of the same key from different partitions, right? So what we do is we add them up together to get the final count of that word. Note that because C and V have the same type, which is integer, and here the C, V, or C1 and C2, they're just variable names. So we can write we can use this same lambda or same function for the two different for both merge value and merge combiners, if you like. It doesn't matter, it's the same. All right, so let's look at another example. Now we want to compute the max value by keys. So in this case, let's assume that we have the scores, let's say, for different students on different courses. So the key would be the student ID, and the value is their score. So basically, for one student, it took he or she took multiple courses, therefore has multiple scores. We want to know the maximum ones, right? So in this case, what is say? Say is also a score, right? So let's say score is a float. So C and V again has the same type. All right, and key is the student ID. Now, in order to create the combiner, what is done to the single row when it is first met? So when it is first met, the the maximum score is itself. So the function here would be lambda. So the function here should be the v itself. All right. And for merge value, what is done to a single row when it meets a previously reduced row? So previously reduced row, the C here is the maximum score that we have retrieved or we have scanned so far, and V is a new score here. So what we do, given this C and V, is that we get the max value between C and V as the output. Right, so that is this max CV comes from. So what is done for merge combiners? What is done to two previously reduced rows? So we have C1 and C2 from different partitions. They correspond to the same student, the same key, and we want to know the maximum value so C1 and C2 are the maximum value of that key in that partition, in their own partitions. So what we do is we get the maximum value of C1 and C2 as the final result. Right. So this is how we get this function here. If you still remember, we have said, sorry, this should be example 3. The C and V can be different. So in this example, we compute the sum and count for the key. Let's see. Let's see the key value pairs would be again the student ID and the score. Right. So when we have the sum and count for each key, for each student, we would be able to compute the average score of that student. So here, the C, the combined type would be sum and count. Okay, so now let's think about how do we get a sum and count for the records of SID and score. So basically, for sum, we actually do the we add up all the scores, we get the sum, right? And for count, for each record, we plus 1. Sorry, for each record, we plus 1. That's how we get the final count value of of the number of, the record corresponds to a single key. All right. So this time, let's try to design the 3 functions from bottom to up. Right. So for merge combiners, what do we do when we have 2 previously reduced rows? So we have C and C. Remember, each C is a sum count tuple. So this is C0 and this is C1, right? So for sum, we have a sum from different partitions corresponds to a same key. So what we do is we add them together, get the sum of across different partitions. And for count, we also have a count from different partitions to the same SID. That's why we also add up the count together to get the final count. So this is what we do for merge combiners. Now for merge values, what shall we do when a single row meets a previously reduced row? So V is the single row, the score for the single row, and C, again, remember it's a sum count tuple. So for that tuple, given V here, we should add V to the sum and add 1 to the count. Right? So this is how we get this function here. Now we consider a create combiner, which is what we do for the single row when it is first met. In this case, as it is the initialize of C to some extent, given this key value pair and the value itself, now the sum is the value is itself, and the count is 1 because we only have this one record. So that's why we use lambda v of v1 as the create the function of the create combiner function. Okay. Now let's use some real data to see how combine by key actually works in Spark, right? So let's say the data is formed like this. They are partitioned into 2 partitions, where you can see a B actually across partitions. All right. So we do create combiner and merge value in each of the partitions. So we handle each of the partitions first, then we merge partitions together, which we will use merge combiners. Okay. So for partition 1, we have A2, A4, A9, and B10. So for A2, as it is the first single row that we met, so we use a create combiner. That's why we this 2 comes from 2 here, and 1 is the count, right? And for A4, because this is a single row that meets a previously reduced row, so we use merge values. And then we have this accumulator A is C here actually. So the C and the 4 is A's value. So this is V. So we have 2 plus 4 as the new sum and 1 plus 1 as the new count, which comes to 6 and 2. So for the same reason, we've got 15 and 3 here. Now for B, for B equals to 10, because B equals to 10, this B is a new key, right? So B10 is a single row that it is first met. There's no previous reduced row that we can combine them together, right? So we use a create combiner, and we have 10, 1 here. All right. So for partition 2, please note it here. When we have B20, it is again a new row that we firstly met, because this B10 is in another partition. So in this partition, B20 is a new row. That's why we use a create combiner for B20 here. And for the same reason, I mean, we use a create combiner for these 3 here. For this Z5 and Z8, we do the similar things to A4 and A9. So that's what we have in 2 partitions. So as you can see, the only two functions executed is create combiner and merge value. Now we merge partitions together. We have this accumulator A. Sorry, I've made too many marks. Let me change the color. Okay, we have accumulator A equals to 15.3. Accumulator B equals to 10.1. Accumulator B 21 here, and accumulator they 16.3 here. Right. So we have only one A here. We just put it here. One they here, we put it here. We have two B's. Right. That's why we need a merge combiner. We have one from here, the 10.1, and one from here, the 21. So this is from partition 1, this is from partition 2. Then we sum the sum together, we sum the count together. That's why we get 13.2 as the result of B. Right. And then if we do the collect, then we will get the result. This is what we get. Again, I mean, the whole procedure will be executed, will not be executed until we call collect. All right. As I have mentioned before, combine by key is a fundamental function in Spark, and it is also a basis of many other functions. So reduce by key is an example here. By the way, reduce by key itself is commonly used. See, so the functionality of reduce by key is to merge the values for each key using a function. So this is the input parameter of reduce by key. For example, if we define the function is like this, then basically the reduce by key will do the summation of for a key. It will sum all the values together as the final value corresponds to that key. Right. So the relationship between combine by key and reduce by key is that you can actually write or implement. In fact, reduce by key is implemented by combine by key. I have the evidence here. So if we look at the source of reduce by key, you can see it actually calls combines by key. Simply calls combines by key. So for create combiner, it just use V as it is. And for merge value and merge combiners, because the functionality is the same, no matter it is in a same partition or across different partitions. That's why we use this input parameter func for merge value and merge combiners. So this is how we implement reduce by key by based on combine by key. Right. Since we have talked about reduce by key, it is worth mentioning group by key as well. So basically, a group by key will group the values for each key in the RDD into a single sequence. But please pay attention that a data shuffle according to the key value in another RDD. So these are all partitions. All right, these are all partitions. And for group by key, it actually do no combining in each partition. For example, it will not combine this A1 together. Although, sorry, there is no although, because group by key will return a single sequence. So this is not the output of return group by key, but these are the output of group by key. So basically it will output a sequence of, the key is A and the value is a sequence which is 6 ones, and the same for B. Right. So if we look at reduce by key, it actually combines before shuffling. As you can see here and here. In this case, it only needs to transfer 2 records for partition 2 and 2 records for partition 3. Right. But in group by key, it actually need to transfer 4 records for partition 2 and 6 records for partition 3. Therefore, using group by key is usually much slower than reduce by key. That's why we suggest you to avoid using group by key when you design the map. So this group by key, reduce by key example is just one of the many examples regarding the efficiency of MapReduce in Spark. So as you may notice, even for a simple word count, we have showed different ways to do the programming, to write the MapReduce code. And the most important thing is the efficiency. Here I list several factors that would affect the efficiency of MapReduce in Spark. There could be more, but so far I think these are most important factors that we should pay attention to. And also for the in the first project, we do have a requirement for the efficiency of your implementation. All right. So first factor is the number of transformations. Because for each transformation, no matter wide or narrow, it involves a linear scan of the whole dataset or the whole RDD. So each transformation you need to go through the whole dataset for once. So which means if you can finish the job in 2 transformations, let's say, you don't make it 3. Okay? Because every time a new transformation involves a new linear scan of the whole dataset. This is especially important when the size of the dataset is large. And the second factor is the size of transformations. You can imagine this is your original dataset. If you use, for example, filter to reduce the size of the RDD, the next time when you call a new transformation, the cost will, if we say, say here we have L1 records, here we have L2 records, and L2 is smaller than L1. The next time you call a transformation, the cost will reduce from L1 to L2. Or let's say, for example, in this case, let me see, we should do, yeah. So in this case, it is, the total cost would be big O of L1 plus L2. But, let's say we do the filter as the final step. then the cost of linear scan would be 2 times L1, which is larger than the previous case. So control the size of the transformations and try to make the size as smaller as earlier, try to make the size smaller as possible, as earlier as possible, is the key to reduce the time cost of MapReduce Spark. And the third thing is shuffles. So basically, data transferring between partitions is costly, especially when we consider a cluster of work nodes, right? So because this involves disk I/O, network I/O, and data serialization and deserialization, right? So in order to do that, there are a couple of ways to achieve the goal. So first off, for example, if we can reduce the number of data transferring between partitions, or say across partitions, for example, ideally the best way is the partition data from partition 1 goes to partition 1, from partition 2 goes to partition 2. But sometimes data from partition 1 goes to partition 2, and this as well. The more data transferred across partition, the higher cost it occurs. But if we can reduce the number of data transferring between partitions, say like this, then it is better. Another so one way is to we re-partition such that we can reduce the transfer across different partitions. Another way is we reduce the size of the partitions. Now, in this way, the number of transfers between cross partitions will be reduced as well. Right. Now let's look at a couple of examples here. For example, here this example shows how do we reduce the number of transformations and as well as shuffles. Right. So assume that we want to have both the sum and the max value of a given key, right? And the data is a set of character count pairs. All right. No, character count is not good. Let's say it's ID and score. Right. So a bad design would be we firstly get the max by key, this RDD, which requires a combine by key, which requires a shuffle. Right. And then we get a sum by key, which needs another combine by key, brings another shuffle. Remember, the shuffle is as well as a transformation, right? And then we join these two RDD together and finally get the sum max RDD. Here we get another shuffle and transformation as well. So in total, 3 shuffles. Now, a good design is to use one combine by key to do the two things at the same time. All right. In that case, we only need one shuffle and we finish the job. So even these are not shuffles, just transformations. I mean, for example, in the first, let's see the values are strings, let's say. In the first transformation, you make all the characters to be into lowercase, and the second transformation, you take the first three characters from that string. Okay, so you need 2 transformations, but actually you can do it in one transformation where you lowercase the string and take the first 3 characters. So in this case, you only need to scan the whole data set for once instead of twice. So this is the example of how to reduce the number of transformations and also the shuffles. And another example is how do we deal with the size of transformations. So here, let's see, we have this word count. Sorry, we need to do this word count problem, but with an additional condition, saying that we only count those words that starts with T, right? For example, if we have a sentence like this is the example, then we actually we don't care about the count of is an example. We only care about the count of this and that, right? And of course, you would have other sentences here. Now, a bad design would be you use reduce by key to count the occurrence of all the words and use a filter to filter those to prune those words that is not starting with T, right? Because let's say you have in total n words. You have n words in the data set, and you have only T words starts with T. So apparently T is much less than n. In this bad design, okay, the total number of records that you have scanned would be 2n, right? And in this good design, where you do the filter first and then you do the count. So you firstly filter prune all those words that are not starting with T. In this case, it's a linear scan of n records, and which leaves you only T records, right? And these T records will be doing reduce by to get the count. So the total number of scanned records would be n plus T, which is smaller than 2n. Not mention that because reduce by key is involves shuffle, or it is a wide transformation, and filter here is it's a narrow transformation. So the good design actually involves less shuffle compares. Well, as one last example today, let's look at how partition would help to improve the efficiency of MapReduce tasks in Spark. All right. So we still do a word count kind of task with the additional condition that we actually group them by the second, based on the second character. So for example, if we have this is the as, so what we do is we'll actually output H2 and S2. All right. So a bad design would be would do a reduce by key first to count the occurrence of each word, and then do a map to map the key, which is a word, to its second character, and then do a reduce by key based on the new key, which is the second character, and get the final count. Right. A good design here is to firstly partition the data into different partitions, but based on their second character. For example, this and the would be partitioned in one partition, and another partition probably contains is, as, such kind of words, right? Then we do reduce by key, and also the map and reduce by key. By the way, this is not the best way this is not the best design here, because we actually do not need to use two reduce by key. Actually, we could use one map and one reduce by key. Sorry, so here should be here should be partitioned RDD using a map and then reduce by key. But anyway, the purpose here is to show that if you have if you have partitioned the RDD based on the second character, the reduce by key here and the map here and the reduce by key here would, although reduce by key conceptually is a wide transformation, but here it would be act like a narrow transformation, right? Because we have already partitioned and put all the words with the same second character, the same second character in one partition. So there would be no such kind of data transferred across different partitions, and hence improve the efficiency of the MapReduce task. All right. So that's pretty much for today's lecture. We have introduced MapReduce in Hadoop and MapReduce in Spark, and we particularly focus on MapReduce in Spark. We discussed use combine by key as an example to show some idea of how to design a MapReduce program in Spark, and we also discussed the factors that could affect the efficiency of MapReduce tasks in Spark, and how do we improve the efficiency to make a good design, right? So that's all for today. See you on Wednesday.